The star that became an atom. There is a dead star in the universe that refuses to behave like death. It no longer burns like the sun. It no longer shines because fusion is alive in its heart. It is not a planet, not a normal star, and not yet a black hole. It is something caught between matter and catastrophe. A sphere only about the size of a city, but heavier than the sun. A corpse so dense that a sugar cube-sized amount of its matter would weigh more than a mountain. A spinning remnant so extreme that its surface can move at a significant fraction of the speed of light. A magnetic engine so powerful that, from across the galaxy, it can blink at us like a lighthouse built from the bones of a dead sun. This is a neutron-star, but the name is too quiet. It sounds like a category. It should sound like a warning, because a neutron star is not simply the remains of a star. It is what happens when gravity almost wins completely, but matter makes one final stand before becoming a black hole. To understand it, do not begin with the dead star. Begin with balance. A living star is a negotiation between two enemies. Gravity pulls inward. Fusion pushes outward. Gravity wants to crush the star into itself. Fusion, deep in the core, releases energy that pushes back. Hydrogen becomes helium. Later, in massive stars, heavier elements begin to form. For millions of years, the star survives because neither side fully wins. That is what a star really is. Not a peaceful ball of light, a war held in balance. But every war of this kind has a fuel supply, and when the fuel changes, the balance changes. A star like the Sun will not end as a neutron star. It is not massive enough. It will swell, shed its outer layers, and leave behind a white dwarf. That is dramatic, yes, but not the kind of violence we need for a neutron star. For a massive star, the death is deeper. As the lighter fuel runs out, the core contracts and heats. New reactions begin. The star burns heavier elements. Each stage is faster than the last. The star becomes like a clock, accelerating toward its own destruction. Hydrogen can burn for millions of years. Later fuels burn for far less time. Then the core reaches iron, and iron is the wall. This is the first mystery. Why does iron kill the star? Because fusion is useful to a star only when it releases energy. That released energy is the pressure holding gravity away. But iron is different. Iron is near the point where fusion no longer gives the star the energy it needs. It is nuclear ash. The star has built the very material that ends its own life. Once the core becomes dominated by iron, the engine fails. Fusion can no longer support the weight above it. The outward pressure collapses. Gravity, which has waited for millions of years, finally gets its chance. The core falls inward, not like a building slowly weakening, like nature removing the floor from beneath reality. The collapse is so extreme that ordinary atoms cannot survive. Electrons are forced into protons. Together, they become neutrons. The empty space inside atoms is crushed away. Matter is compressed until it approaches the density of an atomic nucleus. An object once larger than Earth is squeezed into something only miles across. The outer layers of the star are still rushing inward, falling toward the collapsing core. Then the collapse rebounds in a violent explosion. Neutrinos carry enormous energy. A shock tears through the star. The outer layers are blasted into space. We call this a supernova. For a short time, one dying star can outshine an entire galaxy. But the explosion is not only death, it is distribution. The star throws its elements into space. Carbon, oxygen, silicon, iron, the ashes of stellar burning are scattered into the galaxy. Future clouds will use them. Future planets will use them. Future bodies will use them. The universe wastes almost nothing. But at the center of the explosion, something remains. Not a normal core. Not ordinary matter, a neutron star. Now comes the second mystery. How can something the size of a city weigh more than the sun? The answer is that the familiar structure of matter has been destroyed. You think matter is solid because your hand cannot pass through a table. But atoms are mostly emptiness. Electrons form vast clouds around tiny nuclei. The solidity you feel is not fullness, it is force. A neutron star takes that emptiness away. Electrons and protons have been crushed together. Atomic structure has collapsed. Matter has been forced into a state where the usual distances between particles are gone. It is not merely packed tightly, it has become a new kind of object, a star-sized atomic nucleus. That is why the density is almost impossible to imagine. If you took a teaspoon of neutron star matter, it would weigh billions of tons. The comparison is imperfect because neutron star matter cannot simply be removed and placed politely on Earth. It exists under the crushing conditions of the star itself. But the image tells you what the mind needs to understand. This is matter with nearly all ordinary emptiness removed. And because the gravity is so intense, even light must struggle to leave. Light leaving the surface is bent by the star's gravity. In some cases, you could see more than half of the star's surface at once, because gravity curves light from the far side around toward you. Imagine looking at a sphere and seeing part of its back. That is not illusion. That is space-time bending the path of light. A neutron star is not a place where common sense survives. Now comes the third mystery. What is inside it? The outside is already extreme, but the inside is worse. The outer crust may contain iron nuclei, squeezed into a rigid lattice with electrons moving through it. Go deeper, and pressure rises. Nuclei become richer in neutrons. The usual architecture of matter begins to deform. Then, near the bottom of the crust, the particles may arrange themselves into bizarre shapes. Long rods, flat sheets, tangled structures. Physicists call this nuclear pasta. It sounds almost funny, but the material is not funny at all. It may be among the strongest substances in the universe. Spaghetti-like and lasagna-like structures of nuclear matter formed not in a kitchen, but in the pressure chamber of a dead star. Even a tiny mountain on a neutron star could be only centimeters high and still contain astonishing mass. But beneath the crust, certainty begins to weaken. There may be neutron superfluid, matter flowing with almost no friction. There may be superconducting protons. There may be exotic phases of nuclear matter. Deeper still, perhaps neutrons dissolve into quarks. Perhaps strange quarks appear. Perhaps matter becomes something for which our everyday language has no good name. This is why neutron stars are not only astronomical objects, they are laboratories. Gravity has built an experiment we cannot build on Earth. The only problem is that the laboratory is light years away, hotter than imagination, denser than mountains, and wrapped in gravity strong enough to bend light. So we study it indirectly. We watch how it spins. We watch how it cools. We watch how it pulses. We watch how it merges with another neutron star and shakes space-time itself. The universe hides the experiment, but it lets us read the shadows. Now comes the fourth mystery. Why do some neutron stars blink? A neutron star is born from collapse, and collapse does something remarkable to rotation. If a spinning object shrinks, it spins faster. A figure skater pulls in their arms and accelerates. A star collapses from an enormous sphere into a city-sized remnant, and the same principle becomes cosmic. The neutron star spins rapidly, sometimes many times each second. The fastest known examples can rotate hundreds of times per second, faster than the human mind can comfortably picture. A point on the surface may race through space at a large fraction of light speed. But spinning alone does not create the blink. The star also has a magnetic field. During collapse, the magnetic field is compressed and intensified. What was once spread through a massive star becomes concentrated inside a tiny remnant. The magnetic poles can launch beams of radiation. And if those magnetic poles are not perfectly aligned with the spin axis, the beams sweep through space as the star rotates. If one of those beams crosses Earth, we see a pulse. Flash, silence. Flash, Silence. The star is not turning on and off. We are simply standing in the path of its rotating beam. That is a pulsar, a lighthouse made from a dead star. The first time humanity found one of these signals, it did not look like a dead star. It looked like a mystery. A pulse arrived from the sky with astonishing regularity, again and again, like a cosmic heartbeat. Not random, not messy, not the ordinary flicker of stars. Something was keeping time in the darkness. At first, the signal was so strange that people wondered, half seriously, whether it could be artificial. A signal that precise feels almost intentional. Nature is often violent, but here, nature seemed disciplined, ordered, repeating. But the universe did not need aliens to explain it. It needed a spinning corpse of a star, a neutron star with beams sweeping through space, a pulsar. This is one of the most beautiful lessons in astronomy. Sometimes the strangest signal is not a message from intelligence. Sometimes it is matter obeying physics under conditions so extreme that obedience looks like design. A pulsar is a clock made by collapse. And once we understood that, neutron stars became more than theoretical remnants. They became observable machines. Their pulses allowed us to measure their rotation. Their timing allowed us to test gravity. Their changes allowed us to learn what happens when matter is packed near the limit of collapse. But neutron stars do not always live alone. Now comes the next mystery. What happens when a neutron star has a companion? Many stars are born in pairs. They orbit together, age together, and sometimes die in ways that remain connected even after one becomes a compact remnant. A neutron star may orbit a normal star. If the companion is close enough, the neutron star can pull material from it. Imagine the smaller dense object stealing the atmosphere of a larger star. Gas spirals inward. It heats up. It emits powerful radiation. The neutron star feeds, but feeding is dangerous. If the neutron star gains too much mass, the balance that holds it up can fail. The same object that once resisted complete collapse may finally cross the limit. Gravity wins the last argument. The neutron star becomes a black hole. This is one fate, but there is an even more dramatic one. Two neutron stars can orbit each other. Two dead stars, both impossibly dense, both spinning through space-time, locked in a slow dance that cannot last forever. They lose energy, not through ordinary friction. There is no air in space to slow them down. They lose energy by sending ripples through space-time itself. Gravitational waves, the orbit shrinks. The stars move closer, the dance becomes faster. For millions or billions of years, the motion may seem patient. Then, near the end, patience disappears. The two neutron stars whirl around each other faster and faster until the final collision becomes unavoidable. Now comes the most violent question. What happens when two objects, each denser than atomic nuclei, collide? For a moment, the universe creates a laboratory no civilization could ever build. Matter is ripped apart under gravity and speed beyond normal imagination. Space-time shakes. A burst of gravitational waves travels outward. Some material may be thrown into space. A short gamma-ray burst may appear. A bright fading glow can spread across the electromagnetic spectrum. This event is called a kilonova. Not as bright as every supernova in every way, not simple, not gentle, but rich with meaning. Because in the debris of that collision, something extraordinary happens. Heavy elements can form. This is the next mystery. Where does gold come from? Not the gold in stories, not the golden crowns, the actual atoms. Gold is not easy for the universe to make. Light elements can form in the early universe. Stars can fuse elements up to iron through their lives and deaths. But the heaviest elements require special conditions. Many neutrons, enormous energy, and violent environments where atomic nuclei can grow rapidly before they decay. Neutron star mergers provide exactly that kind of environment. In the chaos of the collision, neutron-rich matter is thrown outward. Atomic nuclei capture neutrons rapidly. They transform. They decay. They climb the periodic table into heavy elements: gold, platinum, uranium, elements that later drift through space, mix into gas clouds, and become part of future stars and planets. So when you look at gold, do not only see wealth, see violence remembered by matter. A ring on a human hand may contain atoms born when two dead stars destroyed each other. That is not poetry pretending to be physics. That is physics becoming poetry. The universe does not make beauty gently. Often it makes beauty by catastrophe, then waits billions of years for minds to notice. This is why neutron stars matter so much. They are not just the end of massive stars. They are part of the recycling system of the cosmos. A star lives, it burns fuel, it creates elements, it dies in a supernova, it leaves behind a neutron star. Later, two neutron stars may merge, creating even heavier elements. Those atoms drift into space. Gravity gathers them into new clouds. New stars form, new planets form, chemistry becomes richer, and eventually, somewhere, life may appear. This means the neutron star is not only an object in the sky, it is part of your ancestry. The iron in your blood came from stellar death. The calcium in your bones came from ancient cosmic processes. The heavy elements in technology, medicine, and civilization may carry the memory of explosions and mergers that happened before Earth existed. You are not separate from these events. You are made from their consequences. This is the grand cycle. Gravity destroys stars, but destruction spreads ingredients. Collapse makes remnants. Remnants collide. Collisions make elements. Elements become worlds. Worlds become life. Life looks back and asks where the gold came from. And the answer is, from death, repeated until it became creation. Now return to the neutron star itself. It is one of the universe's most honest objects. It hides almost nothing about the seriousness of gravity. It shows what happens when matter is pushed to the edge. It shows that atoms are not the final form of matter. It shows that density can bend light, that rotation can become a cosmic clock, that magnetism can become a weapon, and that death can become a factory for the future. A neutron star is not as final as a black hole. That is what makes it precious. A black hole hides its interior behind an event horizon. A neutron star still speaks. It pulses. It emits radiation. It shakes space-time when it merges. It lets us study matter at the edge of collapse without losing every answer behind a horizon. A black hole says, you cannot know what happens inside. A neutron star says, come closer with your instruments and perhaps I will tell you. That is why these objects are so important to physics. They sit at the border. On one side, normal matter. On the other side, black holes. Between them, neutron stars. Dense enough to challenge the mind, visible enough to study, extreme enough to reveal new laws. But still, they do not give up their secrets easily. We do not yet fully know the exact state of matter in their cores. We do not know precisely how stiff neutron star matter becomes at the highest densities. We do not know all the ways magnetic fields behave inside them. We do not know every path by which neutron stars collapse, merge, or survive. Each observation helps. A pulse helps. An X-ray signal helps. A gravitational wave helps. A kilonova helps. Every neutron star is a locked equation, and every telescope is a small attempt to read the answer. This is why the 2017 neutron star merger was so important. For the first time, humanity detected gravitational waves from colliding neutron stars and then saw light from the same event. It was not one messenger from the universe, it was many messengers arriving together: gravitational waves, gamma rays, visible light, X-rays, radio waves. The same cosmic collisions speaking in different languages. And when different languages tell the same story, physics becomes stronger. That event helped confirm that gravitational waves travel at essentially the speed of light. It supported the connection between neutron star mergers and short gamma-ray bursts. It gave evidence for the creation of heavy elements. It opened a new kind of astronomy, where we do not merely look at the universe, we listen to space-time. This is the future of neutron-star science, not just seeing, listening, measuring, comparing, waiting for the next pulse, the next merger, the next flash, the next ripple. Because somewhere in the galaxy, massive stars are still dying. Somewhere a core is collapsing. Somewhere electrons and protons are being forced into neutrons. Somewhere a star is failing to become a black hole and becoming something almost as strange. A city-sized remnant, a spinning magnet, a nuclear laboratory, a lighthouse in the dark. And somewhere else, two neutron stars are slowly spiraling toward each other, losing energy to space-time itself, preparing a collision that may scatter gold into the future. That is the terrifying beauty of neutron stars. They are born from death, but they do not end the story. They keep time. They bend light. They forge elements. They test gravity. They force us to ask what matter becomes when nearly everything familiar has been crushed away. A normal star is a furnace. A black hole is a prison. But a neutron star is a question made of nuclear matter. How dense can matter become before it disappears? How fast can a dead star spin before it tears itself apart? How strong can a magnetic field become before atoms lose their meaning? How much of our world was born from the collision of things that no longer shine like stars? And perhaps the deepest question is this: how many times did the universe have to destroy something before it could build us? A star died to make the remnant. Two remnants may have died again to make the heavy elements. Those elements traveled through space, entered clouds, formed planets, and eventually became the matter of civilization. The universe does not create in a straight line. It burns, it collapses, it explodes, it collides, it scatters. Then, after billions of years, it gathers the ashes and calls them a world. So when you hear the word neutron star, do not imagine only a dense ball in space. Imagine the final heartbeat of a giant star. Imagine a lighthouse made from collapsed matter. Imagine a cosmic clock spinning hundreds of times per second. Imagine a hidden core where matter may exist in forms no laboratory has ever touched. Imagine two of these dead stars colliding so violently that space-time ripples and gold is born. And then look at your own world, at the metals in your machines, at the elements beneath your feet, at the atoms inside your body. Somewhere in their history is fire. Somewhere is collapse. Somewhere is a star that did not survive. That is the truth neutron stars whisper from the dark. Death is not always the opposite of creation. Sometimes death is the pressure that makes creation possible. What feels more impossible to you? That a dead star can become a lighthouse, or that the matter in our world may have been forged when two dead stars collided? Subscribe to explore more mysteries through the questions that still lead humanity to the edge of reality.